Okay, folks. We are going to go ahead and get started. Today's information on Tuesday. I introduced the concept we talked about what carboxylic acid is, what a ester is, what a primary, a secondary, and a tertiary amide is. We also talked about the physical properties that are related to those compounds. The physical properties are directly associated with whether or not the compound can hydrogen bond and the degree to which it hydrogen bonds. So we talked about the fact that carboxylic acids are going to have a higher melting point and boiling point than will primary and secondary amines, mainly because they have that OH group, which has a larger differential between the electronegativity of the oxygen to hydrogen than the amides, which has the nitrogen hydrogen. The carboxylic acid will have the higher melting points and boiling points, followed by primary amides, then secondary amides. And then you get down to esters and tertiary amides, which have the lower of the melting and boiling point simply because they can only have dipole-dipole process. So that is what we did on Tuesday regarding the information. Today, what we're going to do is we're going to talk about those carboxylic acids, amides, and esters in greater detail. The first thing I'm going to do is I'm going to discuss how the carboxylic acids react to form the esters and amides. Then I'm going to talk about carboxylic acids, and we'll get into their nomenclature, followed by esters and their nomenclature, and then followed by amides. And as we do so, we'll talk about, yes, how to name them, and also we'll talk about the importance of the nomenclature. I can't remember who it was. It was Monday during lab. Somebody asked me the order, which order is more important, and I'll actually answer that because it does come up in this particular chapter. I mean, I generally said exactly the way it describes it here, but we'll outline it in greater detail. Okay, so The first thing we're going to talk about is the formation of esters and amides. Due to the electronegativity associated with the carbonyl group on a carboxylic acid, okay, due to the electronegativity differences forming a very polar bond for the carboxylic acid's carbonyl group, the carboxylic acids undergo substitution reactions. The first thing I want to emphasize is that it is a substitution reaction. So when you have had a class and you've had a substitute, what does that mean?
Something's replacing something else.
Something's replacing something else. In high school, that would have been a teacher replacing a different teacher. The same thing goes with this. If I'm talking a substitution reaction, I'm going to replace one thing with another. And specifically, that thing that's going to be replaced is going to be the hydroxide group. So let's talk about ester formation. First of all, let's just talk in general terms. You're going to take a carboxylic acid, and you're going to react that with an alcohol, and that is going to wind up forming a ester and water. This is the general formula for all ester formations. So it means you need to be able to recognize that you have a carboxylic acid and you have an alcohol. So let's just look at a very simple example. Let's take acetic acid. And we're going to react that with an ethanol group. What happens is, again, even though they're not shown, you do have lone pairs that are on your oxygens here. And what happens is that the lone pair on the alcohol is going to attack that carbonyl carbon. When that carbonyl carbon is attacked, because carbon can only have 4 bonds, initially it is going to kick the electrons in the double bond up onto the oxygen in the carbonyl. But carbonyls are actually pretty good groups. So that lone pair comes back in to remake the double bond. When that lone pair comes back in to remake that double bond, then it kicks off the hydroxide group. So what you wind up making is you wind up making the acetic acid, but now it's going to be attached to the what was originally the alcohol. And then you're going to have water as a product. Now this, we'll talk about more how to name it, but this is called ethyl acetate. And we'll talk more about how to name these in a few minutes. Amide formation occurs by the exact same method. You're going to take a carboxylic acid. You're going to react that with an amine to produce an amide and water. This is going to be true for a primary. It can be a primary amine, a secondary amine, or a tertiary amine. So let's take something simple again. Let's start with acetic acid. And let's react that acetic acid with ethylamine. Again, you have to realize that just like oxygen, even though it's not shown, that nitrogen has a lone pair. And so what occurs is the lone pair on the nitrogen attacks at that carbonyl carbon. It will initially break the carbonyl double bond, but that carbonyl double bond will reform, ultimately kicking off the hydroxide group. So what you form is an amide. Questions? That's how esters and amides are formed. The reactions are identical. The difference is what that initial attacking group is. You will note that in doing this, even though I did not show it, one of those hydrogens did disappear when we made the amide. That's where the water was formed. It's from the hydroxide of the carboxylic acid and a hydrogen off of the amine. So let's look at some examples. The first thing I want you to do is I want you to identify the following molecules. As a carboxylic acid, an amide, an ester, or none of these. The second thing I want you to do is if it is a amide or an ester, I want you to write the reactants. Yes, it's going to be N-ethyl acetamide. We'll talk about naming it a little bit more here in a few. Okay, so let's look at the first one, or let's look at these. You're going to have CH3, C double bond O, NH2. We're going to have CH3, OCH3. We're going to have CH3, COOH. We're going to have CH3, COOCH2, CH3. Let's see. We'll have CH3, COCH3, CH3, CH2, CONH, CH3, CH3, CH2, NH2. Let's go with those.
you scroll it up just
So again, you're gonna name whether it's a carboxylic acid, an ester, an amide, or none of those. That's step number one. And then if it's an amide or an ester, I want to know what the reactants are that it came from. Okay, so let's see how you're doing. The very first one was an amide. To figure out where it came from, basically, we're going to break the NH2 away from the C double bond O. So the left-hand side means that it came from CH3, C double bond O, OH. In other words, we replace that, what we dropped off with an OH. And the right-hand side comes from NH3 because we have to add another hydrogen. I liked this particular exercise because it actually makes you work to figure out whether you've got an amide, ester, or carboxylic acid. In the very next one, if we write it out, it's CH3-O-CH3. So that means that's none of the above. It's not an amide, it's not an ester, and it's not a carboxylic acid because it was an ether. The next one in line, writing it out, is a carboxylic acid. It is acetic acid. So one way to recognize the carboxylic acid is if it's all written out in just a straight format, you're looking for the COOH group. That is the quickest way to determine that it's a true carboxylic acid. The next one was an ester. Again, to figure out exactly what it came from, you're going to break the bond right between the double bond, carbon double bond oxygen and the rest of it. To the side that you has the carbon double bond oxygen, you're going to add a COOH. I'm sorry, you're going to add an OH. To the other side, you're going to add simply a hydrogen. So those are the reactants that it came from. The next one was, again, none of these, and the best way to realize that it was none of the above is to draw it out. And when you drew it out, you would have CH3, C double bond O, CH3, which is a ketone. The third, or the next one in line, is an ester. It's easier to see it if you go ahead and draw out the molecules. So CH3, CH2, C double bond O, NH, CH3. Again, we're going to break it right between the C double bond O and the NH group. To the C double bond O side, we will add a hydroxide. So this is CH3, CH2, C double bond O, OH. We added the hydroxide group. And then to the other side, we'll add a hydrogen. So this becomes NHCH3. So you will notice in all three cases that where I decided that it was an amide or an ester, I added a hydroxide group to the C double bond O side, and I added a hydrogen to the other side. I added a hydroxide to the C double bond O group, and I added a hydrogen to the other side. I added a hydroxide to the C double bond O group, and I added a hydrogen to the other side. The very last one was none of the above because it was not a, it's not a, it's an amine.
On that last amide, could it be written as CH3NH2?
Yes, it could.
Oh.
I was just drawing it out so you could see that I added the hydrogen.
Oh, yeah.
But yes, a lot of times, instead of writing it out, when you see it in a text, you're gonna see it written as CH3NH2 or NH2 CH3. Take your pick.
Okay, I didn't know you could put the extra.
You can write it just like you see it.
It'd be the same just for the.
Yeah.
Oh,
But I wanted to illustrate where the water comes from and how I get back to the reactants. Questions about that exercise?
Yes. I was actually thrown off by you writing it just straight like that. So if we ever see like a C and an O together, it's the carbon.
Not necessarily. But if I see a CON or a COO, then I know it's carbonyl. But why I said not necessarily is because this top one could have been written as a CO group, but it's an ether. So you really do need to write it out. But again, if I see a COO or a CON, I know it's an amide or an ester. Those I can guarantee. It's the others that I have to write out sometimes to figure out what they are.
And the carboxylic acid is COOH.
Correct. Other questions? Okay, so let's just talk about carboxylic acids by themselves for a bit. First of all, we can talk about a reaction. I mean, it is an acid. So it can react as an acid in solution. Meaning, let's go back to the previous class where you had carboxylic acid and you tossed it in water. Because it is a weak acid, the hydrogen can be donated during the process to make a CH3C double bond O, O minus plus hydronium. That is true for all carboxylic acids. All carboxylic acids can behave as an acid in water and donate their proton to water to make hydronium. Now, this is going to be, because it is a weak acid, this is going to set up an equilibrium. So in the previous reactions, I showed you carboxylic acid reacting with an alcohol to make an ester. Carboxylic acid reacting with an amine to make an amide. Well, carboxylic acid, if you just throw the carboxylic acid in water, it's going to react, but it's going to act as a weak acid, and you're going to make hydronium and a base. Questions? So this goes back to what you should have learned in your previous class about weak acids. Now, let's talk about nomenclature or nomenclature. Basically, nomenclature is how it's typically stated in the United States. Nomenclature is how it's stated in England. I worked for an Englishman in my graduate school efforts, and it was nomenclature. So. Okay, somebody asked on Monday, how do you know who is going to be the parent and who is going to be the substituents, given all of these functional groups that we have discussed? Now that we have discussed all the functional groups, including carboxylic acid, ester, and amide, we are now ready to answer that question. Most important is the carboxylic acid. Followed by esters and amides, followed by aldehydes, and ketones, followed by alcohols, thiols, followed by amines, followed by ethers, alkenes and alkynes, followed by alkyl halides, followed by alkanes. If you look at this list, for the most part, not exactly, but for the most part, it is in order of how we discuss these things. We started with the alkanes at the very beginning of the semester and talked about adding halides to those alkanes to make alkyl halides. We then talked about the alkenes and alkynes. We then brought in ethers and thiols and alcohols. And then we went to ketones and aldehydes. Then we brought in the amines. So the amines is the only one that is out of order of how we talked about it all semester long. So the textbook has been arranged according to an increasing importance in those functional groups. increasing importance decides who is going to be the parent chain. So carboxylic acids are always going to be the parent chain of what we talked about. If there's a carboxylic acid, it's going to be the parent. Everything else will be listed as a substituent. Now, if you have an ester and an amide, you're probably not going to have a carboxylic acid anymore. So the ester or the amide is going to be the most important one, followed by everybody else. So this is the actual order of importance with respect to who are you going to name as the parent chain. Now, yes, we could get very, very complicated, but we're not going to do that. We'll keep it down to typically a couple, maybe 3 types of functional groups. When I get into 3, a lot of times it'll be something like a carboxylic acid, ester, amide, somewhere in there, combined with an alcohol and alkanes or the alkyl chains. So we won't get overly complicated. It'll be obvious who the parent is going to be. Now, since carboxylic acids are the most important, let's talk about naming a carboxylic acid. We're first going to describe it using IUPAC naming. Again, IUPAC is the International Union of Pure and Applied Chemistry. They basically came up with a method to name compounds so that everybody in the world understood exactly what compound you were talking about, because we all name it the same way. Now, for the IUPAC naming, you are going to simply replace the E of the alkane with oic acid. Exception would be, there are exceptions to this rule, but in general, it's going to get replaced with oic acid. But one of the biggest exceptions that you need to know is acetic acid, which just gets the ic acid, not the oic acid. That's one of the biggest exceptions you need to know. Now, if an alkyl if it has an alkyl substituent, the chain is numbered. So that the carbonyl oxygen or the carbonyl carbon, I meant, of the carboxylic acid functional group is carbon 1. So let's look at some examples. So if I have CH3, CH2, C double bond O, OH, which I could write this way, or it could be written as CH3, CH2, COOH. They mean the same thing. It's a 3-carbon chain. So it would be propane. But we're going to take the E and we're going to replace it with oic acid. So this becomes propanoic acid. If I have CH3, CH3, CH2, C double bond O, OH. The longest chain containing the carboxylic acid functional group is 4-carbon chain. So that would be butane. But it's got that carboxylic acid functional group, so it's butanoic acid. Because I replaced the E with oic acid. Now I do need to number this one. And again, when you're numbering, your carbonyl group is going to always be number 1. So this is 3-methyl. Butanoic acid. Let's look at one more. We'll look at this one. The longest carbon chain is the 3-carbon chain. So that would be propane. We're going to take that E and replace it, so it's propanoic acid. But we do have a substituent on it, so we have to number this. It's number 1 will always be the carboxylic acid. 2, 3. So this would be 2-hydroxy propanoic acid. Folks, this is what you're going to use if I tell you to name something using IUPAC naming. Unfortunately, a lot of carboxylic acids have common names. Because they were one of the first organic compounds that was actually made and purified and stuff of that nature. You will need to memorize table 17.1 for your common carboxylic acids. Many of these carboxylic acids, especially when you get into like stearic acid and glutaric, and some of the others are going to be precursors to lipids. So you do need to know the common name for them. So again, you're going to need to memorize table 17.1. Now, another important thing we need to be able to do is name the acyl group left over after removing the OH from a COOH functional group. Typically, what happens is the ic acid, or the oic acid is replaced by oil. The exception is the acyl group left over from acetic acid. That acyl group is known as an acetyl group. So, for example, if I have CH3, CH, or COOH, and I wind up with CH3, C double bond O without the OH, this is acetic acid. This is the acetyl group. But if I have, for example, CH3, CH2, C double bond O, OH, this is propanoic acid. Then the CH3, CH2, C double bond O is called the propanoyl group. If I have benzene with a C double bond O, OH, this is benzoic acid. Then if I have just the C double bond O, this is the benzoyl group. So again, the entire thing I'm trying to get here is if you have oic acid, it becomes oil. Oic acid becomes oil. The only exception is that of acetic acid, and it's just the acetyl group.
So this acting is like a substitute.
This is acting as, when we use this, this will be in preparation for something else. Whoops. But you will see the acetyl group listed because we tend to take and use acetyl a lot, or acetate, or acetic acid. That one is one of the few that is very different.
So there's no cyclic name for.
Sure, if I have this would be cyclopentanoic acid. Again, the oic acid would become oil if I have just the rest, so it'd be cyclopentanoyl group. So yes, you can have a cyclo group too. Now, the last type of naming I want to do is dicarboxylic acids. Once you get the carboxylic acids down, folks, the esters and amides, they're not near as difficult. Because carboxylic acid is the parent name. Basically, if you have a dicarboxylic acid, then the ending of the parent name is dioic acid. Substituents. First of all, one thing you'll need to know about this is the carboxylic acids will be on each end. They are always on the end of the chain. They always have to be on the end. So if you have a dicarboxylic acid, you got one on that end and one on that end. Can you have a tricarboxylic acid? Yes. If you have an alkyl substituent, you could technically have a tricarboxylic acid. But most of them don't go past dicarboxylic acids. And if you have a dicarboxylic acid, you're going to have one on each end. And it gets the dioic acid. As far as the numbering is concerned, it will start from the end, from the carboxylic acid, closest to the substituents. And this again is for IUPAC naming. You don't have to put the number because they have to be on the far ends. So for example, if I have C double bond O, OH, C double bond O, OH, the longest carbon chain is 2 carbons. So this is ethane. But we're going to replace the E with dioic acid. So this technically is ethadioic acid. Ethane dioic acid. In this particular case, dioic acid. We don't have consonants next to a consonant. 。 If I had C double bond O, OH, CH2, C double bond O, OH. This is got a 3-carbon chain. So it's going to be from propane. So it's propane dioic acid. If I had C double bond O, OH, C, H, CH3, CH2, C double bond O, OH. The longest carbon chain is a 4-carbon chain. So this is from butane. So the parent is going to be butanoic or butane dioic acid. But I do have to include that methyl group. And when I number it, I want to number from the one closest to the substituent. So this would wind up being 2-methyl butane dioic acid. Now, I'll be honest, we don't use the IUPAC naming for a lot of our dioic acids because many of those dioic acids have a common name, which you will find in table 17.1 that you had to memorize. Such as this first one up here, ethane dioic acid is the IUPAC name, but it's also known as oxalic acid. And so we typically use oxalic acid, which is its common name. This next one, the propane dioic acid is more commonly known as malonic acid. And so you'll learn the common names. The common names are more important. But I wanted to explain how you would name it using IUPAC naming. But we typically buy malonic acid or oxalic acid. We don't buy ethane dioic acid. Questions? Well, I did not get to esters or amides, so that is what I'll be picking up with on Tuesday of next week. So just as a note, scroll down or up?
No, no.
Okay. So just as a note, next week we will be back in the laboratory for lab. We are doing the egg lab, which is a pretty cool lab. On Tuesday, we've actually covered a lot more of this chapter than you may think. Because when we talked about how to make an ester or talked about how to make an amide, that is a separate section. So I've already gone over that. So we won't have to spend as much time on that. When I asked you what were the reactants that when we were naming or identifying whether it was an amide, an ester, and I asked you what the reactants were, that is actually the result of a reaction. So we won't have to spend a lot of time on those reactions for esters and amides. So we've actually covered a lot more of the chapter than it seems. So what we'll do on Tuesday is we'll finish up the discussion of how to name esters and amides. I will start with a quick recap of carboxylic acids, then we'll go to esters and amides. Then we will move on to, let me look at this. 17.2 talks about the acidity of carboxylic acids. I've already talked about the acidity, but we need to go into more detail. We'll talk about the pKa's. Section 17.3 talks about reactions of carboxylic acids to form esters and amides. Again, we've already done that, but we'll just go over it individually again and do a couple of practice problems. Section 17.4 talks about the hydrolysis of esters and amides to make their reactants. We've already talked about that, so I expect to be able to get through 17.4 on Tuesday. So again, we'll do the egg lab, and then we'll do 17.3 and 17.4. And we will actually be almost done with this chapter. So what does that mean? So this week or next week, you do the egg lab. Then you'll do we'll talk about those things in class on Tuesday. So ester naming, amide naming, and the reactions of carboxylic acids, the reactions to make esters and amides, the reaction to hydrolyze esters and amides. On Thursday, we'll talk about polyesters, because that starts getting into forming chains, which is what protein chains and stuff are. Well, they're not polyesters, they're polyamides. But we'll start getting into that. So next week, I actually expect us to start getting into proteins and the amino acids. As far as your other two dry labs are concerned, a week from Monday, we have our last dry lab. And a week from Monday, that reactions lab that you've been holding on to, that one will be due. The dry lab will be due, the last dry lab, and the egg lab. So we'll have 3 labs due that Monday. Yes. 4 + 7 is 11, yes. So you'll have all the information to finally do that dry lab that we've been holding on to. Any questions?
Where's like the information cut off for the next exam? Like, what do we have to know?
I don't know yet. It's pretty close to, it'll definitely be through this chapter and maybe your amino acids. Maybe. I have to look and see.
Okay. So we like chapter 15, 16, 17, and maybe
Part of 18. Okay, I will see you on Monday in lab upstairs.
Oh, also, are we going to be tested on hydrolysis of citric acetyl?
Yes,
Oh, okay.
you will be tested on acetals and esters because they're related to sugar formation.
Oh, it seemed, I might just look at the book. Look at the book, it seemed like there was different rules to regular hydrolysis.
Oh,
Like the citric ones. I don't know, I just thought that there may be some extra steps to it.
it's just, as far as hydrolysis of those, no, you'll be tested on baking acid.
Oh,
I mean,
okay.
baking acetals in the acetal.
Oh, okay, but no hydrolysis. Of the
Not
citric
breaking
ones.
them back down, no, because that is.
Oh, for any hydrolysis?
No, you'll be tested on hydrolysis of amides and esters, but
Oh, okay.
I don't expect to be tested over breaking down the sugars until we get into, the biochemistry.
Oh, awesome. Good to know.
So Dr. Gordon, so for Tuesday, we need to read 17.2, 3, and 4.
Yes.
You're okay.